Hello, and welcome to another analytics learning module from the Click Continuous Classroom. In this course, we'll be covering one of the most important concepts in analytics, hypothesis testing. Our goal for this course is to discuss the basics of hypothesis testing, focusing on formulating hypotheses, computing test statistics, determining p-values, and finally, interpreting the outcome. Hypothesis testing stands as one of the fundamental ideas underlying a large portion of analytics and statistics. Hypothesis testing is an extremely powerful tool for conducting investigations and has been an invaluable tool in many fields from scientific research to industrial applications. So how has hypothesis testing become so ubiquitous in the data world? Let's take a deeper look and uncover the amazing versatility hidden inside hypothesis testing. To start off, let's look at the general process for conducting statistical hypothesis testing, and then we will explore each part in more detail with a simple learning exercise. First, we will need to determine what we are attempting to prove or disprove, and we will use this to formulate our hypotheses. Next, we need to locate or collect the data we are going to use to attempt to investigate our claim we created in the first step. We then compute our test statistic using summary statistic information we derive from our underlying data. Our test statistic can then be translated into a probability with the aid of a reference table. With our probability in hand, we can then circle back to the beginning and conduct the most important step of them all, which is interpreting the probability in context of our initial hypotheses. This is just the general framework. We will expand on each step more as we examine two example scenarios. Our first step in this whole process is to determine what we want to test and develop our initial hypothesis. In statistics, we'd like to call this initial hypothesis our null hypothesis, and it is often abbreviated by the letter H sub 0. Our null hypothesis is our default position about an estimate or effect, assumed to be true unless evidence indicates otherwise. This might sound confusing, so let's think of a few null hypotheses to get some clarity. A pharmaceutical company is developing a new formulation for existing medication. They want to see if it's possible to improve pain relief. They aren't sure if the two formulations have different results, so their initial assumption would be that, on average, both medications have the same amount of pain reduction. We could write this null hypothesis as H sub 0 mu sub relief old equals mu sub relief new. If you aren't familiar with the symbol mu, it stands for the mean of a population. So mu sub relief old is the average pain relief for the entire population who takes the old formulation, and mu sub relief new is the average pain relief for the entire population who takes the new formulation. If we wanted a simpler example, we could examine a restaurant who wants to test a supplier's claim that the average time it takes to cook a loaf of bread is 30 minutes. Their null hypothesis would be that mu sub cook time equals 30 minutes. For both scenarios, we have our starting point hypothesis, but that's only half of what we need. We still need something to test the null hypothesis against. We can achieve this by stating our alternative hypothesis, which is often abbreviated as either H sub A or H sub 1. Personally, I prefer H sub A, but there's no difference between either notation. Our alternative hypothesis is the claim that we are hoping to test and see if there's any evidence to support it being true. In the case of our first example, we have to think about the alternative hypothesis in terms of the goal for the experiment. We have three potential alternatives. The first being that the old medication has greater pain relief than the new medication. The second is that the old medication has less pain relief than the new medication. And finally, we could combine the first two alternatives into one. The pain relief for the old medication is either greater than or less than the new medication. An easier way of stating this is that the pain relief for the old medication is not equal to the new medication. Thinking about these three alternatives, which would make the most sense for the pharmaceutical company? The company is trying to create a new medication and market it as being more effective than the old one. They would want to pick our second alternative hypothesis, which would be the pain relief of the old medication is less than that of the new medication, since being able to draw that conclusion would be most beneficial for marketing their new medication as being more effective. To them, the outcome that the old medication is more effective, or simply the two medications are different, isn't useful for their study. If we think about the restaurant scenario, we'll see something a bit different. we can again list 3 possible alternatives and consider which one makes the most sense in context. The first one, where the cooking time is less than the stated 30 minutes, highlights a potential issue for the chefs not being able to plan when they need to check on the bread and take it out of the oven. Additionally, the second alternative also presents an issue where customers may grow impatient and chefs may take the bread out too early and not have it be fully cooked. Since the restaurant would be interested in both alternatives, we can combine them and choose the third alternative. Cooking time is not equal to 30 minutes. In both scenarios, we select an alternative hypothesis by considering the context of the problem we encountered. The next step in hypothesis testing is data collection. Data collection takes on a lot of different forms and depends greatly on what is being tested. We need to consider our hypothesis to ensure that we are collecting enough information to conduct a thorough test. One very important assumption we are going to make is to assume that in both scenarios our data is roughly normal, and thus we can use standard normal hypothesis equations to conduct the test. Part of this assumption is that we do not calculate a standard deviation from our underlying sample. We simply use the population standard deviation instead. This is not a realistic assumption that would be made outside of these learning exercises. If you are unfamiliar with the normal distribution, please access the QCC Learning module, Understanding Distributions, for more background on this important topic. Our restaurant scenario is straightforward. To compare the speed of bread baking to a constant stated time, we only need to collect 1 sample's worth of data. These values represent the time in whole minutes that it took 20 loaves of bread to be cooked properly, along with the known population standard deviation of 2. The pharmaceutical scenario hypotheses show that we are going to need 2 samples, 1 for each medication, so we can compare the 2 afterwards. So we will collect a sample of 20 for each of the medications. Since these are the 2 separate populations, we will also have 2 different known population standard deviations. This should be enough data for both scenarios. However, for more complex testing procedures, you might have different data needs such as multiple groups or larger data sets. It all depends on what you are trying to achieve with your data. After acquiring our data, we need to begin computing our test statistic, which is a single value that represents the outcome of our hypothesis. Methods for calculating test statistics vary based on what type of data or distribution you are using and how many samples are in your dataset. Let's do this one scenario at a time so we can step through the calculations. For ease of computation, we are going to start with the 1 sample restaurant scenario. The formula for a 1 sample Z test is Z equals the quantity of X minus mu divided by the quantity of the population standard deviation divided by the square root of n. This formula is computing our test statistic by taking our sample mean and subtracting the expected value and then dividing by the population standard deviation. What this achieves is it tells us how much our sample differs from what we expected to occur under our null hypothesis. Let's obtain the summary statistics for our sample so we can plug in the relevant information. First of all, our sample size, abbreviated by the letter n, is 20, since we have 20 records in our dataset. Next, we calculate the sample mean for x bar and get 30.8. We will use 2 as our population standard deviation for sigma. We're missing one last piece of information, mu, which can be found in our null hypothesis. Mu is the value which we are testing to be true, so in this scenario it is 30 minutes. We can plug all this in and get the following equation. Our test statistic simplifies down to 1.79. This is where the tricky part of hypothesis testing comes in, translating a test statistic to a probability or p-value. But before we do that, what does a p-value even tell us? Getting a little more background on p-values will make this all easier to understand. What the p-value tells us is how likely the outcome we observed, or an outcome more extreme than we observed, occurred, assuming the null hypothesis is true. This means a low p-value tells us that our null hypothesis is highly unlikely to have occurred because the probability of it occurring is very small. But how low is low enough for us to start considering that the null hypothesis isn't actually true? The significance level, also known by the Greek letter alpha, defines how strongly our sample has to contradict the null hypothesis before we consider rejecting it in favor of the alternative. The lower the significance level, the more evidence we need against the null hypothesis before we can reject it. Many industries consider a significance level of 0.05 to be a good cutoff value, meaning that if the null hypothesis has a less than 5% probability of occurring based on our evidence, then we should reject that it is actually true. More risk-averse industries like healthcare need more evidence and have been moving towards an even more restrictive cutoff of 0.01 or 1%. Other significance levels can be chosen. 0.01 and 0.05 are the two most common by tradition, but any level can be selected within reason based on the test being conducted. It is important to determine an acceptable significance level before fully analyzing an experiment to avoid potential bias of picking a cutoff that is favorable for the test. We should have done this back in the hypothesis formulation step, but we did it here instead to avoid introducing the ideas of p-values too early. For our bakery example, we'll be using the standard alpha of 0.05, meaning if the test yields a probability less than 0.05, we can be reasonably sure that the null hypothesis isn't true. For our second example, we will use a stricter alpha of 0.01. Now that we have covered the basics around p and alpha values, let's get back to the example we are working on and convert our test statistic into a p-value.
This concludes part 1 of a 2-part video. Please close this browser window, return to the interactive video